Everyone, today we're going to focus on the Proplanner application, and the emphasis in this particular webinar will be on Tugger analysis. Now, there is a full video on what we call unit load analysis, and I'll describe what I mean by those two things here in a moment. So if you needed more than I'm going to cover on unit load analysis, and I will do a quick overview, you might want to check out that particular focused webinar. So essentially, and let me go to the PowerPoint presentation here to get started. When we look at a flow analysis, we see that with the Proplanner application, we have a routing that takes a device to a location and often back. That's what we call a unit load analysis. A fork truck may leave a location, go somewhere in the facility, and come back. And so what we're doing when we generate what's called a routing file, we'll take a look at one of those in a moment, we're basically viewing the flows to and back, to and back, this single unit load fork truck moves. How Tuggers vary is that with a Tugger analysis, we're actually going to take a set of things that we need delivered to a set of locations, and we're going to leave a location and do a delivery, a delivery, a delivery, a delivery, a delivery, and come back, okay? And that's what's really different. Now, what makes unit load or Tugger flows more difficult than unit load flows is that with unit load flows, all I simply need to do is say, hey, I need to deliver from here to here, or I need to go from here to here. They're just 2-point flows. But with a Tugger, I need to figure out what order I should pick up, because they could be pickups as well, or deliver those materials throughout that route. So it's oftentimes referred to as the traveling salesman problem, which is I have to visit a number of locations, and in which order should I visit them? And so the Tugger analysis is essentially addressing that problem. So we're going to come back and look at this PowerPoint here in just a moment, going into detail on Tugger. But I want to just kind of give you a definition of how Tugger and unit load is different. Now, with that said, we're going to actually start with the unit load study because I want this webinar to be able to address the, for people that are not totally familiar with the Proplanner application. So the Proplanner application does work inside the AutoCAD application. It does require a full version of AutoCAD. I'm using AutoCAD 2019 now. If you only have AutoCAD Lite and you don't want to buy a full version of AutoCAD, then you can purchase our AutoCAD OEM application, which essentially for about $1,000, about the price of AutoCAD Lite, will allow our plugin to work. And that's really the difference between the full AutoCAD and AutoCAD Lite. Is a full AutoCAD supports add-ons and AutoCAD Lite does not. So we'll go into Proplanner. I'm just loading the application, and basically I've gone ahead and loaded a drawing, and I'm going to open a routing file. Now, a routing file is just a comma-separated values file, a CSV file, which you could easily edit in Excel, and we recommend you do that. I'm just going to grab the foot-inch unit load tutorial file, just because it's something that you can look at later yourself. You can actually see it when I click on the file. It's actually showing me it's just an ASCII text file, comma separated values. We do have a metric version that is semicolon separated, but this one is comma separated, and I can select it. And then there are other files as well. There's a file on product quantities, on material handling equipment, on locations, even results that you may have done in the past. Now, these files are not required. In fact, you could check them all off and just load the CSV file. What would happen if you opened a routing file, basically a file that says, I want to go from here to here to here to here to here, the software will then mine that file, look in that file, and grab all the unique devices you call out, all the unique products you call out, all the unique locations you call out. And it will go ahead and create a default product, material handling equipment, and location file for you. It'll put dummy values for, just usually one for a value in the fields it doesn't know. And then as you go into the application, you can fill the rest in. In this case, I do actually have those files. They're included with the tutorial, so I've left those check marks on. I select OK. And what we're looking at here is that routing file. Now we can see in the routing file, actually if we were looking in the Excel file, we would see that the first column of the Excel file is a product name, which is basically just a main flow grouping. It could actually be a product name, or it could be a product family, as it is in this case. It can be really anything that you want to discern the flows between, or calculate often flows for. In other words, in this case, when we get our diagram, we will be color coding typically the flows for small pump, unique from large pump, unique from medium pump. So there'll be 3 different colors of flows in this diagram. And then when I get my report, I'll see a report on material flow for the small pump, and material flow for the large pump, and material flow for the medium pump. So once again, if you have different types of things, I know like in semiconductor, we often use pre-metal and post-metal deposition, or in some assembly plants, we use primary manufacturing and assembly and machining as maybe separate categories. And then within each of those flow categories, we would then define product flows. We would have parts in that category that would go from one location to another location. And then once again, this is a unit load study. This is a routing file, a CSV routing file. So as I mentioned to you originally, we've got a housing, it goes from hand finishing to deburr. We've got another housing that goes from bore to hand finishing. We've got a pump base that goes from metal cutting to welding. It's essentially what's happening. Now, we do have this other set of fields on the right called via locations, and they're just normal locations. So actually, one routing line represents actually 2 moves. You can go from one place, in this case, hand finishing, to a what we call via location, storage 2 in this case, and then eventually on to deburr. We usually like to keep the via location being just that, an offline storage location between the source and the consumption. And that mainly because you do have the ability to ignore we call skip via locations. You can see a checkbox here in the bottom left corner. So that allows you to look at how much material handling cost is associated to your offline storage. You can check the box and it gets rid of that, and it routes the material directly from the from location to the to location. If you don't check the box, then the software is going to go via from hand finishing to deburr via storage 2. We can see that we have a method that could be, typically the method isn't a device name. It might be a group of drivers or a single driver. I mean, if you have Carl working in the part of the plant, and that may be Carl's going to move this material, then put Carl in. Or if you're going to put the north dock driver, put the north dock driver in. Or if you're looking at assembly line 6 material handler, put assembly line 6 material handler in here. The method is really who is moving the material. If we go to the methods tab, you can see that we do have the ability to identify a device like a cart or a forklift to the method. So the method would be maybe the person or group of people moving the product material, and then the method type, you can see a cart is using a device called a cart. You can see that the method type, the device, is essentially where the speed and the aisle layer, the layer in AutoCAD to look for your aisles are, and the fixed and variable costs are all defined. Where the method indicates how many people are in that group and what color we look at their flows for and what their load and load times are. And there's some sophistication on how we calculate load and load times. Right now, they're just fixed numbers, 15 seconds to pick up and 15 seconds to drop off. But as you see in the other video, we won't cover that today. You can define processes to get a lot more accurate in your handling costs. So the other thing we have is a container. Once again, you just type in a unique container name. The software will go ahead and add that unique container name to the list. Containers do have sizes. When we're doing Tugger analysis, sizes become important for small lot delivery because we use the size of the containers to determine the volume of containers on the carts to understand the capacity of the carts. Now, the other way that you can do a capacity analysis in Tuggers with containers is to simply record the container as a 1 in size and then look at quantity of containers as opposed to size of containers. So maybe you know your Tugger cart can handle 4 containers or 6 containers versus a volume or size. That would be more like a large lot delivery situation. So both can be accommodated in the software, but that's how we might use the containers. So we have a device, a method of moving the material. We have a container the material's in. We have a number of containers we can move per trip of this device. And we have a number of parts that are found in the container. Now, this is important because you can see that in this case, 300 parts per container, I can move 2 containers at a time, where the software assumes that in this particular case, I can move 600 parts per trip. Now that's important because if I go to the products tab, okay, in the products tab, I have a total quantity that I want to move per unit of time, in this case, a year. So if I need to move 10,000 of this small pump, okay, and these housings or gaskets are actually 2 per, so that means I need to move 20,000 gaskets, okay. Then I come into here, I need to move 20,000 gaskets. I can move 600 at a time. So it takes the 20,000 divided by the 600, and I have my number of trips. The percent of flow determines the fact that 100% of these gaskets on this line take that. If I had 50%, then of course I would take the 20,000, divide it or multiply it by 50% to get only 10,000, and that's how many trips would be taken on this route. Okay, and this is from this location. So this is the containers per trip and parts per container from receiving to where it goes, which in this case is storage 2. From storage 2 to assembly 1, we're moving via a cart, also 2 containers per trip. We don't get to change the parts per container. That's only done once per trip. And then we have a description field on the right if we want. Okay, so the next thing I'm going to do is look at locations. Now in the software, there's a layer. There's actually 2 layers of interest. One layer is the layer in AutoCAD that the text labels, which represent the locations for things, are placed. So for every unique location name that you specify in here, the program will go to AutoCAD's pp_locations layer and look for a text label of that name. Okay, single line text. And so don't use multi-text in AutoCAD. And it will find that text label and record its XY location. Now, it doesn't want to find 2. If it does, it throws an error and tells you to get rid of one of them, or it'll just by default use one of them by randomly selecting. But it's important to recognize that you really only want one of those in there, text, and it just grabs the insertion point of the text and uses that as a location. You can also see that in the locations tab that when I loaded the software, it went into the drawing immediately, went to that layer immediately, found all these text labels on that layer and recorded their XY location. Okay. Now that I have a location for those things, I simply can go into Calc. I have 2 types of flows I can do, straight flow, aisle flow. I select Calc by straight flow. The software went in, and because I did an aggregation by product, which was my checkbox here, aggregate by product here in the bottom middle, right above the Calc button, the software was able to compute the number of trips that I need to take, the distance of those trips, in this case, straight flow distance, and record the total distance, the total time, and the total cost to move those materials. It also recorded the percent of time that I'm moving versus loading, handling. In this case, I'm actually traveling only about 20% of the time, which means 80% of my time is pick up and set down. Okay, so you'll see that'll change a little bit when I tell the software to go to the aisle flow analysis. The aisles are pretty straightforward. You can see these purple lines in here. I went into the software. There's a PES tab. I created aisles. But essentially what's important to note is the aisles are just lines in AutoCAD drawn on a layer. Now, what layer? Well, you specify the layer. So in this case, I create a layer called PF_aisle path in AutoCAD. And I use that same layer for both the cart and the forklift. I could, of course, create 2 different layers and draw lines on those layers. Okay, and then each device essentially goes to a layer, in this case, the same layer. It looks at those lines I drew, which are these purple lines here, and as long as those lines cross one another, an intersection is assumed. So that means that helps the software build a path network. Now, the next thing the software needs to do is to connect the text labels to the path network. Now, you can do that manually, but we recommend you use the software to do it. I'm going to go ahead and erase what I call my aisle joins. Before I do that, I'm going to erase all the drawing paths just to clean up the drawing a little bit. So you can see in this case, there are a bunch of red text labels. I'll zoom in so you can see them a little bit better. And you see there are purple aisle path lines, just lines in AutoCAD that I drew. And then you see there are these red lines that join them. In fact, if I go in here and erase aisle joins, you'll see they'll go away, and they did. Now, to complete the path network to do an aisle analysis, the text label's current position needs to be linked to the aisle network. And you could, once again, do that. The software actually creates another layer of the name of the aisle layer with a join, dash join at the end. So if this layer was, Dave, then I'd have a Dave-join, and that's where these new lines are about to be created. So when I say join locations to aisle, the software finds all those locations, finds the quickest path to get them joined, and creates them. Now, in this case, stage didn't get joined because in my current flow study, stage is not a reference name. It's only going to join locations that are referenced. In other words, join locations that are in the current flow routing study. Of course, if I were to create a routing line that did go to stage, then we would see stage would show up. And I can go ahead and do that. So I can go into this small pump here. I can go and say, I'm going to go from receiving to a location called stage. I could just type stage in if I wanted to. I'll just leave everything else default. I'll add that row. And here I've added that row. Next time I do a calc, I'll have a flow there. But if I were to go into my PAS tab now and join locations to aisle, it's going to find any that are missing and automatically connect them. And you can see in this case, stage was joined. All right, the next thing I'm going to do is do an aisle flow analysis, select calc, and the software will go ahead and generate the flow diagrams. And these case now I have much longer travel distances, which means, of course, there's more time spent traveling, less, relatively speaking, less time handling, because my handle time was a fixed time and my travel time was increased. And so you can see the total distance increased, as you would expect, doing an aisle flow versus straight flow, and the time increased. Now note that the time is also, let's just take the first case, 54 hours. That time does not take into account accelerating and decelerating around all these 90-degree turns. In the methods tab, you can see that we can specify a turn angle. In this case, my turn angle is 5. Probably 120 is a more appropriate number for that. And I'm going to use a 50% effectiveness value. But what the turn angle of 120 means is that anything less than 120 degrees is assumed to require the device to come to a stop and then start up again, and a full accel decel. The effectiveness is interesting. Right now, the flow diagram that I have is only tracking productive moves. In other words, moving the material from A to B. It doesn't have, I didn't go into my routing file and estimate the move back or to move to some other location. So if I want to account for the deadheading moves to support my productive moves, I need to add in an effectiveness value, not an efficiency, but an effective. How effective is your device? How often when it travels does it have a load? And for most plants, if you did a work sampling study, you went out and randomly observed your trucks for, let's say, 100 times in a day, and you saw that of those 100 times you observed a moving truck, it had a load, and the other half the time it had a load, 50 of the 100 times, and 50 of the 100 times it didn't have a load, then your truck would be 50% effective, right? So I'm going to update that in this case. And I've done that for the cart. I'll go ahead and do that same for the forklift as well. I'm going to put a 50 in here. I'm going to put 120 for my turn angle, which is what it should be. And we'll do an update and we'll be good to go. Okay, so at this point, I'm going to do another calculation. And what you'll see here, if I look at my results, is look, my travel time is now up to 44%. I was at what, 54 hours? Now I'm at 69, almost 70 hours of handling as a result of adding the, in this case, actually adding to the deadheading. I'm not using the accel decel yet. That's turned off. So when I check that on and recalculate, you can see that now I even need more devices. I'm going to go ahead and say yes, go ahead and increase the device utilization. And you can see now I went from, we were at 54 hours, I'm now at 96 hours. Now that's taking into account aisles, that's taking into account deadheading, that's taking into account acceleration, deceleration. And you can now see that my travel times are what were as low as 20% with a straight flow study that didn't take any of this into account. They're now up to 60%. But it's still important to note that even though we're at about 60% travel time, load and load time represents about 40% of our time, which means that you have to be kind of accurate. You have to be careful to include accurate load and load times in your study. So these are the very basics of a flow study. And what I wanted to do, bring you up to speed with that, is let's now move into, from unit load studies, where we're moving fork trucks, let's go look at Tugger studies. Now to do that, I'm just going to leave this analysis here, and just to not create any confusion here, I've got my tutorial file right over here. I'm going to go from the unit load tutorial on foot inch. I'm going to go into the either Tugger file, okay? directory. And in this Tugger directory that you get with your tutorial files, we have a drawing and we have some Tugger examples. And we're just going to go into there and take a quick look at how to do a Tugger study. Now, a Tugger routing file is a little bit different. In fact, what actually happens with a Tugger analysis is that we take this file, this Tugger file, which we're going to look at here in a moment, and we generate a routing file. So in a way, we're still going to do a calculation with a routing file. But so that you don't have to solve the traveling salesman problem by hand yourself, which is a lot of work, we give you a module, a tab called Tuggers, which allows you to load a Tugger delivery file, we call it, and generate a flow routing file from it, okay? So it's really a pre-processing task that's going on here. Let's load a delivery file just so you can see what I'm talking about. So we're going to grab the Hydropump Tuggers file, also a CSV Excel file. It also has an MHE and a loc that goes with it. We're just grabbing those right now, and here's what that file looks like. Now, what we're looking at here is we've got parts. Once again, they have containers, and we have a certain number of containers we want to move every time we move that part, okay, on this particular, what we call delivery. So you notice this part, some parts are going to show up multiple times. Notice 11,332 and 11,332. That is fine. And they're both going to the same place. But with a delivery file, what we're saying is these are actual deliveries. We're not saying that these are a route that many of these parts are going to be moved on multiple times. We're saying this is an actual specific material move. This material at this time, estimated time of delivery, which is basically 8.7 hours into the day, okay, so be what, about 8:50, around 8:50 in the morning. This part is going to be picked up at a receiving location, 11, and it's going to be delivered to a plant location called Bore. And it's going to go via a staging area. So basically, there's going to be a device that's going to leave the staging area in front of the warehouse. It's going to go into the warehouse and pick up this part at receiving 11, along with probably a lot of other parts. And then it's going to come back out the dock door. And then it's going to go out into the factory and drop this part off at the Bore location, once again, as well as other parts that it's doing. That's the whole point of a Tugger study. The key thing is that I just want this part delivered around 8:70 a day, okay? And we'll talk about some of these other things as we go on. We do have the ability to specify a load unload time specific to this delivery, as opposed to assigning a default to the device. If there is no time specified in here, the software will use the method's load and load time. But if you want to override the load and load time assigned to the method, you can specify it here. By the way, the same is true for the unit load flow study. There is a field in the routings tab where you can specify the load and load time for a specific route. I can also call out a route driver directly. I can say I want to use this fork truck Tugger driver or this fork truck Tugger route. So I can manually assign a route driver to this particular delivery. Or more importantly, I can let the software figure that out. Now you might want to ask, well, how does the software figure that? How does the software know if I have multiple Tugger drivers in my plant, which one should do this delivery? Well, the answer is pretty simple. It goes into the locations tab. In the locations tab, you can see there's my locations and my location positions, X and Y, just like you saw before. But what you didn't see before, I didn't talk about, is the fact that I can map a route driver to a location, just like imagine the Postal Service mapping a mail person, mailman, mailwoman, to an actual address home. Now this mapping can be done by just simply selecting a bunch of locations and going in here and going into routes here and going into here and mapping it here and picking update. Or you can also go into AutoCAD, okay, and window a bunch of locations like I'm doing here, maybe grab some of these as well, okay? And you'll notice, if you can see, I'm not sure you can, but there's little shaded areas where some of these locations have been selected and some of them haven't. And then go ahead and map them to a particular route driver graphically, okay? Now that's a much more, I guess you'd say, common sense way to do it, because most of the time you're going to want to pick a region in the plant, a set of locations that you want a route driver to serve. Now it's in this locations tab also where you're going to define your route drivers. You're going to go in here and you're going to create a set of route drivers that you want the software to use. You can call them any name you want, but remember, this is the name of a method, a person that's going to drive around your plant in this area and deliver material. And you typically would give it a different color. So you go and you create these route drivers, and then you go into your locations and you start mapping route drivers to locations. Now that's, once again, if you want the software to automatically map a delivery to a driver. Now you might say, well, how did we do that? Well, once again, if I go under bore, I can say, well, which route driver which is going to do it? I could go specify zone 1 or zone 2. Or I could come in here and say, well, what route driver is currently delivering to bore? Well, we can see up here that the route driver zone 1 is currently serving the bore location. So that's the route driver that's going to get that delivery. Now, the next thing that we need to consider is when the material is going to get delivered, we're going to have time fences. And you can see for the two route drivers that are defined here, zone 1 and zone 2, I've gone in and set a delivery interval. In fact, in this case, I've done a 10-minute delivery interval. That's what this 10 means. Okay, start and interval total. So start and end means that this driver is available from 7 a.m. to 3 p.m., 24 hours in a day, 7 to 15, 7 a.m. to 3 p.m. This driver is available. Otherwise, outside of that time frame, this driver cannot accept a delivery. This driver is going to go out every 10 minutes. Okay, so what we're going to do is we're going to take the day between 7 a.m. and 3 p.m. and we're going to divide it in 10-minute slots, 6 slots per hour. And the software is going to go ahead then and look at when this part wants to get delivered, and it's going to put it in the slot. So the first thing it does is find all the material that needs to be delivered in that time slot. That's the set of things that are going to get delivered in that time slot by the zone 2 driver. The next thing it's going to do is figure out in what order to deliver those materials. Now, the last number is the time to deliver. In this case, it's also 10, which means they have 10 minutes to go out, but they also have 10 minutes to complete their job. They could go out every 10 minutes, but have 20 minutes to do their job. And you might say, well, how is that possible? Well, that would mean that there would be 2 drivers. They're staggered. One driver goes out in 10 minutes, then is out there for 20 minutes. The next driver comes back 10 minutes later, gets on the load and goes out, and they're just tag teaming each other. Okay, this is the volume of material that's being delivered. Once again, the effectiveness of the device. In this case, it's usually 100%. And if there's a staging area that device is specifically assigned to, in this case, zone 2. And so this is, some of the information that gets assigned. So now the other thing I want to talk about is this concept here of statistically generated estimated times of delivery. What does UFM 710.2 and 0.5 mean? What that means is the uniform distribution. So instead of specifying a specific delivery time for a specific thing I want delivered, which, by the way, often can be done by grabbing move tickets from the factory, something that happened yesterday. If you know that all these things were moved yesterday at this time, you could just load that delivery file, that move ticket file, into the software and use what happened yesterday as your actual model for how your Tugger system would have performed in that actual state. So you're using fixed estimated times of delivery. But in a future state scenario, we may not have move tickets. We may not know exactly when that material is going to get delivered. What we do know, in this case, what we're saying is this part, which is 111.847, is going to be delivered between 7 a.m. and 10 a.m. There's two deliveries that need to be made, and each delivery is 1 container. So if I had 2 deliveries and there were 2 containers, that would mean 4 containers would get delivered, 2 on each delivery. But in this case, we're delivering 1 container, but we have 2 deliveries. Now, here's the kicker. Each of those deliveries has a 50% chance of happening. So what that means is we could have 0, statistically speaking, we could have 1, or we could have 2, right? The software will put it into a random number generator and figure out if I'm going to have 0 deliveries, 1 delivery, or 2 delivery. And that's why we have a random seed value down here. You can change the random seed. If the random seed number stays the same, then your answers will be the same, okay? But if you change this number and rerun the analysis, you're going to get a different number of things delivered. Uniform delivery here, 1 and 1. What does that mean? There's one container to be delivered between 7 and 10, and there's a 100% chance that's going to happen. So there will be one container delivered. Or if I had done 4 and 1, that would be 4 containers are going to get delivered in that time frame, and a 100% chance that each of them will be delivered. In that case, there will be 4 containers delivered. There are multiple distributions. We have uniform, we have triangular, and we have sequence deliveries. A sequence delivery means I want a delivery every 30 minutes, okay? So you're going to get N number of deliveries every 30 minutes. Now, there could be a statistical probability on that, which means if I had a delivery every 30 minutes throughout the day, technically there'd be 16 deliveries in an 8-hour day. But if there was a 50% chance of those deliveries happening, then of the 16 deliveries that could happen every 30 minutes, probably only half of them are going to happen. Now, they could all happen right away. They could all happen at the end of the day. They could randomly happen throughout the day. But the point is you have sequenced, uniform, triangular, and of course, a fixed estimated time of delivery. Now, I'm going to start off, as I usually do, with the FAST algorithm for the traveling salesman problem. And I'm going to do a straight flow analysis also, as I usually do, just to kind of get an idea of what's going on here. Now, before I do that, let me go back to the PowerPoint and just show you what we're doing and why we're doing it, okay? So once again, the objective is, this is a particular route driver, okay, this red route driver, who had a delivery at multiple locations here in the plant and came back. And in this case, I did what's called a figure 8. I did a from stage 2, which means I'm starting by a driver is grabbing a cart, going into the warehouse, filling their carts, coming back out, going out in the plant, delivering the materials. Same person. Now, in some companies, there is a person that fills the carts. In the warehouse, there's a person that delivers the material out on the line. 2 different people. In that case, I would just do the stage from to stage, or I would do the stage to 2. I would have to do 2 different Tugger studies, evaluating each of those people individually. But if they're the same person, then obviously I want to include all the work to the same person. And so those are some of the 2 different things that we can do. The problem here is that, let me go to